Hi everyone, welcome to this demonstration of the Secant Lines exploration tool, which I developed and it's available on my website. Today what we're going to do is look at this function f of x is equal to x cubed minus 5x. And we have an a value of -2, an h value of 4.5 to start with, and a scale of 7. So what's going on here is you can change this function, the x cubed minus 5x, to anything else that you'd like. But let's go ahead and start with this. And let me explain just quickly what is going on. First, there's this red dot right here, which is on the graph of the function. Notice there are two red dots. So the red dot that's on the left it has x coordinate -2, and that's what this a value is. So that explains what a is, but what's h? Well, h is the distance between this point and this point in terms of x coordinates only. So not the actual distance along the red line here, but if you just look at the x coordinate here and the x coordinate here, if you were to subtract the two, you'd get 4.5. And the scaling is just if you need to zoom in, and we'll discover that we will need to do that a little bit later. The idea of this is as follows. So we have this fixed x value called a, which is -2, and we go 4.5 units to the right and look up or down to see where is the graph of the function. In this case, it happens to be up here. And we draw these 2 points. So the first point is -2, 2, and the next one, the x value is a plus h, or it's -2 plus 4.5, that is positive 2.5. And then we apply f to it, or get the y value on the graph, and that happens to be 3.125. And basically between these two red points on the graph, just draw the line between them. That's the secant line. This secant line happens to cross the graph at other places, like right here. We can't really control that simply because this graph happens to be just that wavy. But we can take these 2 points and compute the slope of this line. Right? This is a change in y over a change in x. And here we get a quarter. Now the real story of calculus is to now take this h value and just make it smaller and smaller. So we have 4 right now, 4.5 now. Let's make it 4. So I just erased the 0.5. It didn't change at all yet. What you have to do is change what you'd like, and once you're happy, click outside of your current input box. Click somewhere else. And we see what was actually a very drastic jump in the slope of the line. Our earlier slope was actually positive, and now what happened is actually due to the sharp drop in the y value of the function. By just moving a little bit over, by reducing the gap in the x value and the x value just by a little bit, we have a new point down here. This point stayed the same, and we graph that new secant line that we have, and it has a slope of -1. Now, if we shrink the h value even a little bit more, it looks like, just due to the shape, it looks like the slope will even become smaller than -1. So let's try that. Instead of 4, let's replace it with 3.5, 3.5. Click out of here to update. And indeed, the slope went down a little bit more. We can continue this, maybe 3. Let's just skip along, maybe 2. Excuse me, I don't know what happened here. We can make it 1. We can look at probably 0.5. Maybe the red dot will end up somewhere over here. It's kind of hard to tell. Maybe the slope will go up, maybe it'll go down. If it just passes beyond here, if the red dot will be drawn to the left of here, then the slope should go up. Right? So let's try that. Let's try 0.5. So this current slope is 2, and when we click out, we see, oh, that is a pretty drastic change. The slope is now 4.25. Now, if we make h even smaller and smaller, I think what we'll see here, just based on how sharp, how steep the blue graph is and how quick the changes in y, I think we'll see even bigger and bigger changes to the slope, at least for a little while. So this 0.5, we could actually just write, instead of 0.5, we could use 1 divided by 2. If we click outside, nothing should change. We see the same secant line drawn, nothing changed there. But now it's maybe a little bit more convenient to do something like 1 over 2 and then change that to 1 over 3 and 1 over 4. And now it's hard to see what's exactly going on. This is a good time, maybe we can change the scale. Currently with the 7, it's looking at this point right here and going 7 units out this way and 7 units out this way, 7 units up and 7 units down. This is probably a good time to let's change the scale to maybe, I don't know, maybe 2 might work. Let's see what happens. And yeah, it looks like we can get a little bit better picture of what's going on here from a scale of 2. Maybe that's even too much. Let's change that to a scale of 3. Okay, so now what happens, because the blue graph is actually, it doesn't really change a whole lot here. If we change from this red dot to another red dot on the blue graph, probably not a lot is going to change here, right? The slope, it looks like because the blue is slightly to the left, the slope might increase a little bit. So let's try, it's 89 over 16, whatever that is. But let's try changing the h value to 1 over 5. And yeah, the slope, who knows quite exactly what's going on. But the point is we can pay attention to these slope values. So 1 over 5, let's cut to the chase, maybe 1 over 50, maybe 1 over 500. And just quickly estimating based on what these fractions look like, the 2 red dots that are drawn now by the computer are so close it's really hard to even see what's going on. Maybe we have a chance of seeing what's going on if we change the scale to actually something like 1 over 100. And maybe we don't. But that's the point. So as these 2 red dots get closer to each other, that still makes sense. We can draw a line between any 2 dots. But the thing is, as we pay attention to the slope, the limit, if you will, as we'll discover, is going to be closer and closer and closer. The limit of these slopes that we see will be the slope of the thing that we discovered on day 1. That was the tangent line. Alright, let's zoom back out. Let's go back to that scale of 7. Let's even reset h to, what was it, 4.5. We'll just use 5 because we're a little bit lazy. And let's go ahead and look at another function, right? So we could, for instance, look at cosine of x. That's a perfectly fine function. And we'll get a graph of what's going on here. I guess, using an a value of -2, it's not very useful for cosine. It's just hard to see what's really going on. Why don't we make sure that we use nice values, probably nice angles for our a value? How about just 0, right? So that moves our sort of fixed point to be 0, comma, whatever cosine of 0 is, and that's 1. So that's the point we'll look at here. And then h also, it'd be nice if since h is going to end up being the gap, it'll be the distance between, actually for that reason, I'd like to change a. To illustrate the point a little bit better, I would like to choose, let's see, the period here is 2 pi. I'd like to choose pi as the a value. So let me just type pi. There we go. Okay, so now we have the point pi comma -1. That it will be our fixed point. That will always be a point that determines the secant line. And then the other point, well, that'll depend on the h value. And h, remember what happens is if we look at the x-coordinates of the 2 red points, then they will be this distance away. Right now, 5. So 5 is just not quite a good number to use. We really ought to use, just so that the numbers work out and all these calculations look nice, we should try to use h values that will give us nice angles for the input of cosine values that we'll know very well. So let's go ahead and try something like h is pi over 3. That should be totally reasonable. And when we look at h is pi over 3, then what this is saying is we started with this a value, the x value here, was a, which is pi, and then the new x value we're going to look at is pi, that's our a value, plus pi over 3, so we'll get 4 pi over 3, and that's what this is right here. And then we're going to apply f to it, so that's cosine. Cosine of 4 pi over 3 is -1/2, and so we plot that point. So we get these 2 points which are on the graph of the function, and draw the secant line. Now the fact, again, that this red secant line crosses to the blue graph somewhere else is just a matter of sheer coincidence. It just happened because the graph of cosine was, too wavy. So what is going to happen as we decrease the value of h? And in fact, it's kind of already hard to see what's going on. Why don't we change the scale here from 7 to being something like maybe 3 will work? Yeah, that'll probably be, well, maybe even 2. Let's try 2. So as we decrease the value of h, what do you think is going to happen? Maybe you'll pause the video for a second and think about that. So what happens, let's see, so let's try h's, we have pi over 3, maybe we'll try pi over 6. I don't know if we're going to get much nicer values than this. So let's try a smaller number than pi over 6, since pi is about 3. Pi over 6 is, I guess, about a half. Let's try numbers like then, well, 0.5, something smaller, maybe 0.3. Okay, what about 0.2? Now it's hard to see what's going on again. Let's zoom in a little bit. Let's make this a scale of 0.5 in each direction. And let's change h again to be smaller, 0.1. And as we keep doing this, it looks like the slope here is going to level off, and the slope will be 0 eventually, right? We can't expect the slope to become negative by doing this because all of the points to the right of this red point, so we have these 2 red dots, and all the points on the graph which are to the right of the left red dot have y-coordinate which are going to be bigger. So the slope will always be positive, but it just gets smaller and smaller and smaller. We could start verifying this by just placing a bunch of zeros in front. This forces the 2 values to be very close to each other. Okay, great. And the other thing we can do, if we just zoom back out a little bit, let's change the scale back to something like 6. We can also use h values that are negative, something like maybe -4. That means we have, this is still our fixed point, but now the other point, we find its x value is, take this x value and subtract 4 from it, and then just find the point that's on the graph of the function. We can make h -3, h -2, h -1, and we see now what happens is the slope of these secant lines is always going to be negative, but if we go h is -0.5, -1/3, and so on, we'll again discover that the slopes of the secant lines is now increasing from this negative number and getting closer and closer and closer to 0. Okay, the only thing you can't do with this is choose an h value of 0. Now I forget what happens if you do this. Aha, I did program this in here. You can't choose h as 0. If you choose h as 0, you get this little warning, this friendly warning which says, hey, choose h to be non-zero to see the real power of this tool. Alright, thanks for watching. We'll talk more about this throughout the rest of Chapter 2.